Alright guys, I'm going to teach you today via video because I am currently involved in a week-long session, so I tried to get out of it for tomorrow, but it's been fucking crazy, so I couldn't get out of it. So, unfortunately, I couldn't get another professor to cover the class, so I just drove back to Murfreesboro and I'm going to teach here in this great empty classroom to the camera, which I've never done before. So it might be a little weird, but we're just going to wing it and see how it goes. I don't have a whole lot to go over. Basically, just a little bit of review on the circuit stuff from last time and the new stuff, which is decibels. So again, I know that you should have at this point looked at parallel and series circuits and series parallel a little bit, but something that I really want to hammer home is the concept of the electrical load, which we talked about a little bit ago, and that is just simply this, right? If we have a simple circuit with a voltage source over here, and we have a resistance over here, we are going to have a current flow through the circuit, right? It's going to flow through here. That's our current. And we know all of this is expressed through Ohm's law, which we've defined as V equals V equals I times R, right? So we have that. That's our Ohm's law and the simple circuit accompanying it. And we know from looking at parallel and series circuits that the way that we look at total voltage, total resistance, total current, all of that's going to change depending on how we arrange resistors in series and parallel, or speakers, or anything that has an impedance. But right now, just looking at the simple circuit again and talking about load, we need to look at the resistance in terms of its effect when we have a constant voltage source. So if I write V equals I times R over here, and we have a fixed voltage, right? This is always going to stay the same, and the resistance goes up, right? The current does what? It's going to go down proportionately to keep the voltage the same. If the current goes down, it means less work's being done and we have a lighter load. Therefore, more resistance is less of a load on the amplifier or whatever is providing our voltage. And then, of course, vice versa. If we have the resistance go down, it's going to draw more current from our device, therefore increasing the load. Okay, so that's something that we talked about a little bit ago, and that is that. I just kind of wanted to talk about that once more, because really that's the biggest kind of stuff that you need to take away from the circuit fundamentals, the electricity stuff that we've been doing. Okay. All right, moving on from that, we're going to cover some new stuff. I'm not going to go crazy in depth into this, partly because it's super late at night and my brain is fried, but also what we're talking about, I think, should be fairly straightforward for y'all, and should be a little bit of a review from audio fundamentals, hopefully. So the next kind of big mathematical stuff that we're going to dive into is, transducer sensitivity, be it a microphone or a speaker, input or output, all that kind of stuff. And when we talk about that, we talk about it in terms of decibels, which obviously we are familiar with, right? So the decibel, before we dive into like its application and more specifics with it, we're just going to talk about the math that the mathematical abstraction of it before we get to like how it applies to theory. Okay, so when we're talking about decibels, we've really got two flavors of decibel math that we're doing. We have decibels that are concerned with pressure, and we have decibels that are concerned with power. All right, so if we're talking about pressure, be it acoustic pressure or electrical pressure, we're going to use the 20 log formula. So if I want to find out how many decibels something is, and I want to know how many decibels in volts or dBV, I can represent that as 20 log X being a voltage, and the V reference is 1 volt. So let me rewrite that a little bit. So this would be our V, and then the reference we're looking at is 1 volt. So all this equation is showing us really is 1 volt being the reference. If we have, say, 4 volts, what does that mean in terms of dBV? Okay, so it's just a way of representing voltage differently. Sorry, I'm off camera. I forgot to get the calculator out before we started. So, just like frequency and stuff like that, we are talking about a nonlinear scale. Decibels are logarithmic. You can see the log right here. So I can't just say 4 volts is 4 dBV. That's not true. That's not how this works. So if I wanted to figure out the voltage for this, I can just simply put 4 volts over 1 volt inside this logarithm, multiply that by 20, and that's going to give us a voltage expressed in dBV. Okay, so if we did that, 4 over 1 is 4, so dBV, this is kind of unnecessary, this 1 volt, but I'll put that there just so you know that there is a reference. We'll get back to that. So 4 over 1 is 4. Take the logarithm of that, multiply that by 20. Okay, so 4 volts is 12 dBV. Okay, so real simple, should be, right? We solve the inside of the parentheses first. In this case, there's a 1 in the denominator, so it's easy. Then we take the logarithm of that, we multiply that by 20, and we have our result over here. So what we found was 4 volts expressed in dBV. Okay, so now let's say instead of dBV, we want to look at dBu. And on your little formula sheet, equation sheet thing, you'll see there are many different flavors of decibels inside of the pressure and the power. So if we change from dBV to dBu, which is a different way of representing voltage, okay, instead of using 1 volt, we're using 0.775 volts, or 775 millivolts. And once again, we just have V as the numerator, so we're looking at this voltage compared to our reference, and in doing this process, we will find out what our voltage is in dBu, okay? So let's say 20 log, we have 4 volts again. Our reference this time is 0.775 volts instead of 1 volt. That's something that you guys kind of need to log in your head. So if we do that one now, that's a little bit less easy because there's not a 1 here, but still pretty straightforward. Just divide 4 by 0.775, take the logarithm of that, and multiply it by 20. Okay, so we have 14.2 1.25 dBu. That's our final answer there. Okay. So that's the pressure side of this. There's a another way of looking at pressure or decibel change, and that is just simply the change in pressure between 2 points. So if we, instead of caring about dBu, if all we're worried about is the change in decibels, delta dBu, or dB, again, sorry, delta dB, we can just look at 20 log of V2 over V1. Okay, so what is V2 and what is V1? That's going to change depending on the scenario, all right? So if I said I have a preamp and it is outputting 10 volts, and I then change the gain, the knob on the front, to 15 volts, I want to know how much of a change in gain it was in dB, just dB, not dBu, not dBV. So instead of using a fixed reference for our dB equation, we're going to use whatever the first voltage was. In this case, in the preamp, let's just say 20 log of 15 volts. That was the voltage that we changed the preamp output to, and the original voltage was 10 volts, okay? So you can see here we're just looking at this compared to our reference, if you will, the reference being 10 volts. So 15 over 10, take the log of that and multiply it by 20. We'll do that real quick. So if I do that, I get something like 3.52 dB. Again, no dBu, no dBV. We are just simply concerned about the relationship between these two numbers. The first number, V1, being our kind of reference voltage for that particular equation, and our V2 being the new thing that we changed it to, okay? So that's all well and good. That's pressure for you. So if we look at power on the other side over here, power is very similar. The only thing that changes is what goes in front of the logarithm. So instead of being 20 log, it's 10 log. Let's look at the same thing. Instead of looking at 15 volts over 10 volts, we're going to look at 15 watts. Looking at power now, power in watts, 15 watts over 10 watts. We're going to use the same numbers with this equation just to see the difference that the power side of this gives us. So again, simple, 15 divided by 10, take the log of that, multiply that by 10, okay? So instead of multiplying by 20, all you do is multiply by 10 to get the power. So if you do that, you're going to end up with 1.76. Okay, so that is exactly half of this pressure, and it should be, okay? So the change in power, the scaling of the decibels for power, it's a different thing than for pressure. That's why we use the two formulas, okay? And you know from doing the Ohm's law and that kind of stuff that power and voltage are not the same thing. We know that because voltage times current gives us power. So these are two fundamentally different concepts in terms of how you express decibels and decibel change, okay? So there's that. We did the pressure side of this. We did the power side of this. That's decibels for you. That's the math side anyways. And that's really the big stuff that we needed to cover today, because until we start talking about the concepts, this is just more math, okay? So before we go, though, I am going to do a little bit more math. We're going to stick mostly to the pressures, but we'll dabble in some power as well. I just really quickly want to run you through some kind of staple I guess, decibel numbers. So let's look at the change in decibels when we double the voltage, okay? So if we just say our reference voltage is 1 volt and our new voltage is 2 volts, right? We doubled 1 volt to get 2 volt. Let's figure out what the change in dB is. Okay, so 2 over 1 is 2. Take the logarithm of 2, multiply that by 20. Okay, the change in dB is equal to 6 decibels. This is hugely important. If you double pressure, be it electrical or acoustic, dBSPL, dBV, dBu, any of those, if we double the pressure, this value here, right, we went from a reference of 1, we doubled that to get 2. If you do that, then you're going to get a 6 dB increase in gain. And vice versa. If we had 1 in the numerator and 2 in the denominator, we halved the voltage, we halved the pressure, we would get negative 6 dB, okay? So all that would change, 20 log of 1 over 2 volts, is the sign. The change in decibels is the same. We just went down 6 dB. Okay? So that's an important number to keep in your head. All right? So if we know this for pressure and we just looked at how we did it for power, you can kind of guess that the change in decibels is going to change with the same relationship. So if we look at the change in dB for power, should have left the board divided. If we look at this, though, 10 log of 2 watts over 1 watt, the change in dB is going to equal 3 dB. Again, if we look at the change in dB in terms of lowering the power, our reference is 2 watts, we went to 1 watt, we halved the power. Our change in dB is going to be negative 3 dB. Okay? So those are the decibel fundamentals. That is really all I wanted to cover today. The online practice should be fairly simple. It's just calculating decibel values, looking at an unknown quantity here. We don't know the pressure, but we know what the decibel value is, or we know this value, we know the pressure, we don't know the decibel value. Before we go, real quick, I'll do one where we have a decibel value, but we don't have this value here, just so you've got that. All right, so again, if we have a problem, say on your online practice that says, I have 10 decibels of gain change, for instance, the preamp, we turned it up 10 dB. What voltage is, like, what's the new output voltage of the preamp if the original output voltage was 2 volts? Okay. So our unknown here is the actual voltage here. It's not the decibel value. We know that. We're looking for the voltage that would give us 10 dB of change, right? So here, we divide by 20 on both sides. 10 over 20 is just 0.5. Okay, 0.5 equals the log of x v over 2b. This is the point, if you remember back to the first day, I kind of demoed one of these problems. This is the point where you're going to use the little anti-log button on your calculator, which should look like 10 to the x, because that's what we're doing. We're saying what value gives us, if we raised x, if we took 10 and raised it to the xth, power, x being the log the anti-log of this, if that makes sense. Okay. So, basically what we're doing, it's really hard to explain this on 2 hours of sleep. But that's all right. All you need to know is we're doing the inverse of a logarithm, really. So if we take the inverse of the logarithm, we're saying 10 to the x, x being 0.5, that's going to give us the inverse of this, okay? So we're going to take the log out. We're going to take 10 to the 0.5 over here equals xv over 2v. You do that side, and then you multiply by 2. All that by 2 gives us something. And that something is 10 divided by 20 to give us 0.5. Take the antilog, 10 to the 0.5 is 3.16. And then, if we simply multiply that by 2, we get 6.325, something like that. Is that in dB? Hint? No, it is not. 6.325 what? 6.325 volts. Okay, so 6.325 volts is X here. If we had a preamp that was originally outputting 2 volts and we changed it so its output was at 6.325 volts, we would have changed the gain on the front by a positive factor of 10 dB. Okay, so that's everything to do with the decibels. We looked at power decibel, we looked at the pressure. Remember, doubling pressure is 6 dB increase, doubling power is a 3 dB increase. Having them is just a negative, so having the pressure is negative 6 dB, having the power is negative 3 dB. We've got all of that. We did the math for solving for our unknown decibel. We did the math for solving for our unknown new voltage if we had a reference and our decibel. So that should be everything you need to do your homework. So sorry about missing class this week. Hopefully I'm going to get it arranged so that I am basically clear to teach on Tuesdays and Thursdays from here on out with the studio. So I'll try and get that taken care of. All right, thanks for joining me.